Welcome back. Right now we will be discussing instantaneous velocity. So in the past, in the last lecture, we had talked about uniform motion, which meant that velocity was constant. Well, that's a fairly interesting situation, but it's fairly limiting as well. We can't really do much with it. What's even more interesting is to see what happens when an object's velocity changes. Now, this could mean that either the object is speeding up, slowing down, or if the direction is changing. So in all of these cases, our velocity changes. Because of this, we'll need a way to discuss what the velocity of an object is at any instant of time. We'll call this the instantaneous velocity. Notice at the beginning of the graph here, we have a shallow slope here, and this indicates a very slow speed or a small velocity. And as time progresses, the object is speeding up, the velocity is increasing, and the slope of the position versus time graph gets steeper and steeper. Okay, so from now on, anytime I use the word velocity, I'm going to be, I mean instantaneous velocity. Okay, so if we take a zoom in of the graph at the point 0.75 seconds, we see that it's curved here, but I want to know what the instantaneous velocity is. Well, if I zoom in on this, I see that it really actually kind of looks like a straight line. And I can approximate a delta x and a delta t for this small portion of the graph. So to find the velocity at this time, so in other words, to find at a time t is equal to 0.75 seconds, the velocity, which we know is defined as the change in position or the displacement over some time interval. In this case, our change in position is 1.6 meters divided by 0.2 seconds, the horizontal time, and 16 divided by 2 is 8 meters per second. So we can see the velocity in this case is in fact 8 meters per second, just as we found before when we had a constant velocity. This is the slope of that curve at the point t equals 0.75 seconds. Graphically, we can say the slope of the line, the slope of this curve at any point is the same as the slope of the tangent line at that point. Now, if you've taken calculus before, you know how to find the tangent line to a curve quite simply. For those who haven't taken calculus, we're going to approximate this by drawing a line that just touches the curve at the point and finding the slope of that straight line. So once again, in this case, now here's our triangle, right? Our delta x, the vertical displacement, is 8 meters. You see that here. And this time interval is 1 full second, 0.5 to 1.5. If I were now to say that our velocity is equal to 8 meters divided by 1 second, again, we get a velocity of 8 meters per second. This was an approximation, but we actually did a pretty good job calculating the exact velocity at that point in time. So, as it turns out, we saw before that if we took the area under the curve of a velocity graph, this corresponds to the displacement of our object. So remember, the slope of the displacement graph is equal to the velocity, while the area under the velocity graph is equal to the displacement. These two graphs are interrelated. So the rule holds even if the velocity graph is curved. Let's take a slightly simpler picture. So here's a velocity graph where the velocity steadily increases. We have a constant increase in velocity. It could be, for example, a car pulling away from a stop sign and going faster and faster and faster. How far does the car move during the first 3 seconds? Well, we said that the displacement is the area under the velocity graph. So we need to find the area of this triangle. Well, we can simply use geometry to find the area. So delta x is equal to the area under there. And remember the area of a triangle, that's 1/2 times the base times the height of my triangle. So that's 1/2. My base now is 1, 2, 3 seconds. don't forget your units, times the height, well, that's 12, see that? And that corresponds to 12 meters per second. Well, 12 times 3 is 36, divided by 2 is 18 meters. Now let's look at our units. The seconds cancel, and I'm left with 18 meters. So my displacement, delta x, is equal to 18 meters. That's how far the car went in the first 3 seconds of his acceleration. So that was our only example for this section. And now on to the next section.